Welcome back. In this video, you will learn how to solve certain types of trigonometric integrals. Let's get to it. Alright, so we are going to focus on learning some techniques that will allow us to solve trigonometric integrals in these two forms. Our first form is the integral of sine to some power m of x times cosine of some power n of x times dx. And our second form is the integral of secant to some power m of x times tangent to some power n of x times dx. And for both of these forms, we are going to be looking at integrals where at least m or n is a positive integer. And so in order to do this, in order to solve trigonometric integrals of these two forms, we are going to need to manipulate them into a form where we can use u substitution and then the power rule of integration in order to solve. Because in most cases, in the form that they will be given to you, they aren't going to be possible to solve without any manipulation. And that manipulation that we are going to do is going to involve using some trigonometric identities. And so before we look at any techniques on how to solve either of these forms of a trigonometric integral, we need to look at some important trigonometric identities. And the first type that we are going to look at are the Pythagorean identities. And so in this box, we have our Pythagorean identity for sine and cosine. We know that sine squared x plus cosine squared x is equal to 1. And from that identity, we can solve for sine squared x and cosine squared x. And we would find that sine squared x is equal to 1 minus cosine squared x, and cosine squared x is equal to 1 minus sine squared x. And then in this box, we have our Pythagorean identity for secant and tangent, where secant squared x is equal to 1 plus tangent squared x. And from that identity, we can solve for tangent squared x and find that tangent squared x is equal to secant squared x minus 1. Now, it's important to note that for these identities, that as long as the angles inside both of the trig functions are the same, the identities will apply. So let's say we had sine squared of 2x and cosine squared of 2x, that would still be equal to 1. And so if you had sine squared of 2x, you could say that that is equal to 1 minus cosine squared of 2x. All right, so if you have a different angle other than just x, remember that the identities will still apply, you just need to include that same angle to the other trig function in that identity. And of course, that also applies to this identity over here for secant and tangent. All right, so keep that in mind because that's going to show up in trigonometric integrals. All right, so those are the Pythagorean identities that you need to know. Those are going to help you solve both forms of integrals, where you have sine and cosine and secant and tangent, but the next set of identities are only going to apply to sine and cosine. And so here's our other set of identities that you want to know. These are the half-angle identities, and like I said, I only have the identities for cosine and sine because these are the only two identities that you're going to need in order to solve most of the trigonometric integrals that you are going to encounter. And so we have that cosine squared x is equal to 1/2 times 1 plus cosine of 2x, and we have sine squared x is equal to 1/2 times 1 minus cosine of 2x. All right, and so it's important to note here that the angle for cosine squared x and sine squared x, right, this x is going to be doubled in the cosine for that part of the identity, okay? So if you had cosine squared of 2x, that angle of 2x would become 4x in this cosine if you use this identity, right? You would have 2 times whatever that angle is from cosine squared x. All right, so keep that in mind that when you use these half-angle identities, that angle is going to double if you're switching from cosine squared x or sine squared x into these forms. All right, and so with that, those are the half-angle identities that you need to know. Those are going to be helpful for solving some trigonometric integrals with sine and cosine in them. All right, and so now that we have looked at all of the identities that are going to be helpful in solving trigonometric integrals of these two forms, let's look at the general guidelines for how we are going to solve the first form that we have here, which is the integral of sine times cosine, where each of them are raised to a power. All right, so in general, these are the guidelines that you want to follow when you are solving an integral of this form where you have sine times cosine and each of them are raised to a power. What you want to look for is an odd power for either sine or cosine, right? So if you see a power that is an odd number, like 3, 5, or 7, and so on, what you want to do is break up those odd powers for m or n And then you're going to use your Pythagorean identities to rewrite that integral in a certain way. And we're going to look at examples of this, but if you don't have any odd powers for m or n in your integral, meaning that both of them are even, like if both of them are 2 or both of them are 4, then you are going to want to use half-angle identities to rewrite your integral rather than Pythagorean identities. All right, and so let's take a look at our first example problem so you get an idea of what I mean by breaking up odd powers and using the trig identities that we looked at earlier. All right, so here's our first example. We have the integral of cosine to the third power of x times sine squared of x dx. Okay, and then on the side here, I have our identities for us to reference. I have the Pythagorean identities and the half-angle identities for sine and cosine. And so over time, you're going to want to know these by heart, but when you're just learning how to solve these integrals, it might be helpful to just have a list of these somewhere for you to reference. But eventually, you should try to memorize these identities if you can. All right, and so if we look at this integral here, and we look at the powers of cosine and sine, notice that the power for cosine is odd. We have this power of 3. And so since that power is odd, we are going to split that up. And what I mean by that is this. We can rewrite this integral to be equal to the integral of cosine times x times cosine squared x, and then multiplied by sine squared x dx. Right, so cosine to the third power of x is the same as having cosine to the first power times cosine to the second power. If we were to multiply these two parts together, we would get back cosine to the third power of x. Okay, and the reason we do that is because now we have cosine squared x, which we can rewrite using one of our identities. Specifically, we're going to use the Pythagorean identity for cosine squared x. Right, when you split an odd power, you're going to then want to use a Pythagorean identity to rewrite your integral. And so if we write cosine squared x with 1 minus sine squared x, our integral will look like this. We'll have that this is equal to the integral of cosine x times 1 minus sine squared x times sine squared x times dx. All right, and so now that we have rewritten our integral using the Pythagorean identity for cosine squared x, we are now ready to use u substitution to solve this integral. And what that will allow us to do is easily solve the integral with the power rule for integration. Now, it might not initially seem obvious how we're going to do that, but note that when you use u substitution, whatever you set equal to u, its derivative needs to be found within the integral. And so in this case, if we were to set u equal to sine x, note that the derivative of sine is cosine, right? So we would have du dx is equal to cosine x, which means that du would be equal to cosine x dx if we multiply both sides by dx. And so we can replace cosine x dx with du and replace sine squared x here and here with u squared, right? Since u is equal to sine, then sine squared x would be u squared. And so if we rewrite this integral in terms of u, we'll have that this is equal to the integral of 1 minus u squared times u squared times du, right? We replaced cosine x dx with du, so those two parts are gone, and we just have this du, and then we replaced each of these sine squared x with u squared, since u is equal to sine x. And now what we can do is distribute this u squared through this quantity, and we'll have that this is equal to the integral of u squared minus u to the fourth power times du. And now we have an integral that can easily be integrated using the power rule of integration. Okay, and so if I clean up my work here, we can integrate each of these terms. So we'll have that this is equal to u to the power of 3 divided by 3 minus u to the power of 5 divided by 5 plus c. Right, so the power rule of integration says that we add 1 to the exponent and then divide by that new exponent. So u squared becomes u to the third power divided by 3, and u to the fourth power becomes u to the fifth divided by 5. Okay, and so now all we have to do to finish solving this integral is replace u with what we set it equal to, which is sine x. So our final answer is that this is equal to sine to the third power of x divided by 3 minus sine to the fifth power of x divided by 5 plus c. All right, and so that is the solution to this trigonometric integral. Without manipulating this integral in the way we did, we would not be able to solve it otherwise. And so that's why it's important to try and rewrite the integral using one of your identities. Let's take a look at another example. So here's our next example. We have the integral of sine to the 5th power of x times cosine to the 4th power of x dx. All right, and so if we look at sine and cosine here, notice that just like with the previous example, we have an odd power for one of our trig functions. We have sine to the 5th power of x and cosine to the 4th power of x. And so since we have an odd power, we are going to want to split that trig function so that we can use our Pythagorean identity. Right, when you're splitting an odd power, your goal is then to use one of your Pythagorean identities. And so if we rewrite this integral, this will be equal to the integral of sine to the 3rd power of x times sine squared x times cosine to the 4th power of x dx. Right, so when you split your odd powers, you want to make sure that one of the parts that you split into is squared because that corresponds to your Pythagorean identities. You can only use these identities if you have sine squared x or cosine squared x. And so, if we break this into sine squared x, then the other part needs to be sine cubed of x, or sine to the 3rd power of x, because then if you multiply these two parts together, you get back sine to the 5th power of x. Right? You would add the exponents to get 5. However, before we rewrite sine squared x using the Pythagorean identity, note that we have another odd power that we can also split up. Right? So if we split up sine cubed of x, we'll have that this is equal to the integral of sine x times sine squared x, and that's still multiplied by another sine squared x times cosine to the 4th power of x dx. Okay, so when you see that odd power, you should immediately want to split that up to form another sine squared x. All right, and so now we have sine x and then 2 sine squared x that together would still be sine to the 5th power of x. But now what we can do is use a Pythagorean identity for sine squared x for both of these parts. But rather than writing it twice, note that we could just rewrite this to be equal to the integral of sine x times sine squared x squared times cosine to the 4th power of x dx. Right, since we have 2 sine squared x parts, we can just write them as one of those squared. Okay, and so if I clean up my work here, let's rewrite this integral by replacing sine squared x with what it is equal to via the Pythagorean identity. And so we'll have that this is equal to the integral of sine x times 1 minus cosine squared x squared times cosine to the 4th power of x dx. And now that we have used that Pythagorean identity, we should be able to use u substitution to solve this integral. And so in this case, we are going to want to set u equal to cosine x. Right, typically whatever trig function shows up in the identity that you use to replace your squared term, that's what you're going to want to set equal to u in most cases. Because if you do that, note that you could rewrite this to be u squared, and this would be u to the 4th power, and the derivative of cosine, if we take that, du dx is equal to negative sine x, and ignoring that negative, sine x can be found right here in our integral. And so setting u equal to cosine x is going to work. We'd have du is equal to negative sine x dx, and then if we multiplied both sides by negative 1, we would have that negative du is equal to sine x dx, and so we could replace sine x dx with negative du. And so if we do that and rewrite this integral in terms of u, this will be equal to the integral of 1 minus u squared squared times u to the 4th power times negative du. Right? We replaced cosine squared x with u squared because u is equal to cosine, so cosine squared x will be u squared. And in the same way, cosine to the 4th power of x will be u to the 4th power, and then we replaced sine x dx with negative du. Okay, and so if I clean up my work here, let's simplify a little bit. I'm going to pull this negative out to the front, so this will be equal to the negative integral of 1 minus u squared squared times u to the 4th power. Now, in order to simplify this, we are going to need to expand this squared quantity. And so in order to do that quickly, I'm going to use a little trick. We will square the first term, then multiply the two terms together and multiply by 2, and then square the last term. All right, so the expansion will look like this. We'll have 1 squared, which is 1, and then we will add 1 times negative u squared times 2, and that will be negative 2 times u squared, and then we will add the square of our last term. So if you square negative u squared, you will have positive u to the 4th power, and then that's still multiplied by u to the 4th power times du. Okay, and so now we can distribute u to the 4th power through this quantity, and this will be equal to the negative integral of u to the 4th power minus 2 times u to the 6th power plus u to the 8th power times du. And then I'm going to distribute this negative back through the quantity, so we'll have that this is equal to the integral of negative u to the 4th power plus 2 times u to the 6th power minus u to the 8th power du. And so now if I clean up my work again, we can now integrate each of these terms using the power rule of integration, and then we can replace u with what we set it equal to, and we'll have our final answer for this trigonometric integral. So this will be equal to negative u to the 5th power divided by 5 plus 2 times u to the power of 7 divided by 7 minus u to the 9th power divided by 9 plus c. Right, so for each of these terms, we added 1 to the exponents and then divided by those new exponents. Okay, and so then if we replace u with what we set it equal to, which is cosine x, we'll have our final answer that this is equal to negative cosine to the 5th power of x divided by 5 plus 2 times cosine to the 7th power of x divided by 7 minus cosine to the 9th power of x divided by 9 plus c. Okay, and so that right there is the final answer or the solution to this trig integral. All right, so here's our next example. We have the integral of cosine squared x times sine squared x dx. Now, if you notice, in this case, if we look at cosine and sine, both of them have an even power of 2, right? Neither of these powers are odd, and so we don't need to split anything up, and we're not going to use our Pythagorean identities. Instead, we are going to use our half angle identities. And so watch what happens if we do that. Remember that cosine squared x is equal to 1/2 times 1 plus cosine of 2x, and sine squared x is equal to 1/2 times 1 minus cosine of 2x. So we'll have that this is equal to the integral of 1/2 times 1 plus cosine of 2x, and that will be multiplied by another 1/2 times 1 minus cosine of 2x times dx. Now if we pull each of these 1/2s out to the front of the integral and multiply them, we'll have 1/4. So this will be equal to 1/4 times the integral of 1 plus cosine of 2x times 1 minus cosine of 2x times dx. All right, and so now notice what we're left with here. We have two quantities, 1 plus cosine of 2x and 1 minus cosine of 2x. What we actually have here is the factorization of a difference of squares, right? Remember that if you have x squared minus 4, that is a difference of squares, and that can be factored to be x plus 2 times x minus 2. Right, the square root of x squared is x, and the square root of 4 is 2, so we can factor this difference of squares with x plus 2 and x minus 2. These two factors here is essentially what we have right here. We have 1 plus cosine of 2x and 1 minus cosine of 2x, and so if we square 1 and square cosine of 2x, we can rewrite these two quantities as a difference of squares. And so let's do that. We'll have that this is equal to 1/4 times the integral of 1, which is 1 squared, minus cosine of 2x squared. So we'll have cosine squared of 2x, and that's still multiplied by dx. All right, and so we're slowly simplifying our integral here, but we can actually use another identity. Note that we have 1 minus cosine squared of some angle. We can rewrite this using a Pythagorean identity to be sine squared of 2x. Right, sine squared of x is equal to 1 minus cosine squared x, which matches up with what we have here, except our angle is doubled. So 1 minus cosine squared of 2x will be sine squared of 2x. So we can rewrite this integral to be equal to 1/4 times the integral of sine squared of 2x. And that's still multiplied by dx. And so now if I clean up my work here, our integral is even simpler now, but we still can't quite integrate what we have here. And so note that we have another even power for sine, And so we can rewrite sine squared of 2x using its half angle identity. We just need to remember to double that angle when we write out cosine of 2x, right? So this will be equal to 1/4 times the integral of sine squared of 2x, which we can rewrite with this half angle identity, which will be 1/2 times 1 minus cosine of 2 times the angle from sine squared. So we have 2x, so we'll multiply 2 by 2x, and then multiply by dx. And so then if we simplify, I'll pull this 1/2 to the outside and multiply it by 1/4. So this will be equal to 1/8 times the integral of 1 minus cosine of 4x times dx. And so now we have simplified our integral to a point where we can now integrate both terms pretty easily. And so what I'm going to do is actually split up this integral into two integrals. This will be equal to 1/8 times the integral of 1 dx minus 1/8 times the integral of cosine of 4x dx. And so if I clean up my work here, we know that the integral of 1 is just going to be x, right? The integral of a constant is just equal to that constant times the variable of integration, which is x. And so this is equal to 1/8 times x. And then we will subtract this integral, which can be solved using u substitution, where we set u equal to that inside function, right? So we'd have u is equal to 4x, which means that du dx is equal to 4. And then if we solve for du, we'll have du is equal to 4 times dx. And whatever du is equal to, we want to be able to find in our integral, but I don't see a 4. So if I divide both sides by 4, we'll have du divided by 4 is equal to dx. And so we can replace dx with du divided by 4 and 4x with u, which means that we'll have 1/8 times the integral of cosine of u times du divided by 4. And if we pull that 1/4 to the outside of the integral, this is equal to 1/8 times x minus 1/32, because 1/8 times 1/4 is 1 divided by 32, times the integral of cosine of u du. Now the integral of cosine is sine, and so this will be equal to 1/8 times x minus 1/32 times sine of u, and then we'll add c. And then to get our final answer, we just have to replace u with what we set it equal to, which is 4x. And so I'll just rewrite this, and we'll have sine of 4x plus c. And so that is the final answer to this trigonometric integral. Okay, and so that was our last example for trig integrals with cosine and sine. Now we want to look at some trig integrals with secant and tangent. All right, so if we want to solve trigonometric integrals of this form, where we have secant to some power times tangent to some power, we're going to follow this strategy or this guideline. In general, if you notice that you have an odd power for m or n, meaning secant or tangent is raised to an odd power that's greater than 1, then you're going to want to break them up. And then depending what you're left with, you may want to use Pythagorean identities, although you may not always need to, because the derivatives of secant and tangent are not as simple as sine and cosine, so u substitution is going to work a little bit differently. And then additionally, because those derivatives of secant and tangent are a little bit more complex, we may even need to break up even powers when necessary in order to use u substitution. And so we'll take a look at that, but let's look at a very simple example of solving an integral of this form first. All right, so here's our first example. We have the integral of tangent x times secant cubed of x dx. And then on the side here, I have our identities for tangent and secant, which we only have two to work with here. We have our Pythagorean identities for secant squared x and tangent squared x. And so if we look at our integral here, note that we have tangent to the first power and secant to the third power, and that power for secant is an odd power, right? So we are going to want to split secant cubed x into two parts of secant and secant squared. So we'll rewrite this integral, and we'll have that it's equal to the integral of tangent x times secant squared x dx. Now at this point, you might want to use a Pythagorean identity. However, we actually don't need to in this case, because if you remember, the derivative of secant x is equal to secant x times tangent x. And so if we use u substitution for this integral, we could set u equal to secant, so we'd have u squared, and the derivative of u, or the derivative of secant, would be secant tangent, which is right here, secant times tangent. And so we actually don't need to use a Pythagorean identity for this integral. And so that's why trig integrals with tangent and secant can be a little trickier than sine and cosine, because they don't follow a specific pattern every time. You need to be a little bit more aware of what is inside your integral and what the derivative of secant and tangent are, so that you know when you need to use u substitution and when you need to use an identity to make your integral solvable. And so in this case, we don't have to use an identity. So we'll say that u is equal to secant x, which means that du dx, or the derivative of u, is equal to secant x times tangent x. And that means that du is equal to secant x tangent x dx. All right, and so we can replace tangent x, secant x, dx with du, and we can replace secant squared x with u squared, because u is equal to secant. All right, so this is equal to the integral of u squared times du, which we can now integrate using the power rule of integration. We'll add 1 to that exponent and then divide by that new exponent. And so this will be equal to u to the third power divided by 3 plus c. And remember that u is equal to secant x, and so our final answer is that this is equal to secant cubed of x divided by 3 plus c. And so that is the solution to this trigonometric integral. Let's look at a slightly more difficult example of a trig integral with tangent and secant. Okay, so here's our second example. We have the integral of tangent cubed of x times secant to the fourth power of x dx. And so in this case, we have an odd power for tangent and an even power for secant. And so let's start by splitting up that odd power for tangent and have tangent times tangent squared. So we'll rewrite this integral and have that it's equal to the integral of tangent x times tangent squared x times secant to the fourth power of x dx. Now in this case, we're not going to be able to use u substitution right after we split up our odd power. We are actually going to need to use one of our identities in this case, because if we set u equal to secant or tangent, we might be able to find our derivatives within the integral, but it's not going to take care of everything in the integral. We're not going to be able to entirely rewrite it in terms of u in this form. And so what we need to do is rewrite tangent squared x, which we got from splitting up our odd power, with a Pythagorean identity. And so remember that tangent squared x is equal to secant squared x minus 1. And so we'll have that this is equal to the integral of tangent x times secant squared x minus 1 times secant to the fourth power of x dx. And now we are closer to being able to use u substitution. We could set u equal to secant, and that would take care of this secant to the fourth power and the secant squared, but the derivative of secant is not explicitly seen in this integral, right? Remember, the derivative of secant is secant times tangent, and so we have tangent here, but what about that other secant? Well, this is what I was referring to earlier with our guideline, that sometimes in order to use u substitution, we will also need to split up an even power. And so watch what happens if we split secant to the fourth power to be secant times secant cubed. We'll have that this is equal to the integral of tangent x times secant squared x minus 1 times secant x times secant to the third power of x dx. Right, so now if we set u equal to secant x, we could rewrite secant cubed of x to be u cubed. We could rewrite secant squared x to be u squared. And then the derivative of u, which is du dx, is equal to the derivative of secant, which is secant times tangent, which we now have in our integral. We have secant times tangent. And so we can rewrite this whole integral in terms of u now. We couldn't do this previously until we used that Pythagorean identity, because if we did that in this step, if we split up secant to the fourth power to be secant times secant cubed, the derivative of secant would be within this integral, but we wouldn't be able to rewrite tangent squared x in terms of u. And so that's why we needed to continue to rewrite this integral before u substitution would work. All right, and so by using that Pythagorean identity and splitting up that even power, we now can rewrite our integral in terms of u and solve. And so if we do that, first let's solve for du here. we will have that du is equal to secant x times tangent x times dx. And so now we can rewrite this integral in terms of u, and we'll have that it is equal to the integral of u squared minus 1 times u to the third power times du. Right, we replaced secant squared x with u squared because u is equal to secant, so secant squared is u squared, and we replaced secant cubed of x with u cubed for the same reason, and then we replaced secant x times tangent x times dx with du, and so that's what we have right here in our integral. And so if I clean up my work here, we can distribute u cubed through this quantity, and we'll have that this is equal to the integral of u to the fifth power minus u to the third power times du. And then using the power rule of integration by adding 1 to each exponent and dividing by the new exponent will give us that this is equal to u to the sixth power divided by 6 minus u to the fourth power divided by 4 plus c. And then if we replace u with what we set it equal to, which is secant x, we will have our final answer that the integral is equal to secant to the sixth power of x divided by 6 minus secant to the fourth power of x divided by 4 plus c. And so that is the solution to this trig integral. Okay, let's look at one more example for this video. All right, so here's our last example. We have the integral of tangent to the fifth power of 2x times secant squared of 2x times dx. Now in this case, you might initially think that, oh, we have tangent to the fifth power, which is an odd power, and so we should split that up. And while normally that would be a good idea, note that in this case, we have secant squared of 2x, and we know that the derivative of tangent is secant squared, and so we actually don't need to rewrite anything here, right? We could set u equal to tangent of 2x, and then du dx, or the derivative, would be equal to secant squared of 2x times the derivative of that inside function, which would just be 2, which means that du would be equal to 2 times secant squared of 2x dx. And other than that 2, which we can take care of, we can find that derivative in our integral. But since we don't have a 2 in our integral, we need to divide both sides by 2. And so we'll have du divided by 2 is equal to secant squared of 2x dx. And then we could rewrite this integral to be equal to the integral of u to the fifth power, since tangent of 2x is equal to u. So we just have that trig function to the fifth power, or u to the fifth power, times du divided by 2. And so this turned out to be a very simple integral to solve, and I put this example here to kind of remind you to remember to identify what exactly is in your integral. Sometimes when we're solving these trig integrals, we get so set on splitting odd powers or trying to use our identities that we forget that some integrals don't need to be manipulated at all. They can be integrated in their current state. And so if you remember what your derivative rules are for tangent and secant, sometimes you will have a simple enough integral that you can just set u equal to one of those trig functions and then be able to rewrite your integral in terms of u and solve accordingly. And so if we solve this integral, we'll pull this 1/2 to the outside. This is equal to 1/2 times the integral of u to the fifth power times du. And then if we integrate using the power rule of integration, we'll add 1 to our exponent and divide by that new exponent to have that this is equal to 1/2 times u to the sixth power divided by 6 plus c. And then we can replace u with tangent of 2x, and then multiply the denominator here. 2 times 6 will be 12, and so this is equal to tangent to the sixth power of 2x divided by 12 plus c. And that is the solution to this trig integral. All right, and so this was the last example for this video, and so what I hope you learned here about trig integrals is that solving them is all about knowing your identities, knowing the derivatives of your trig functions, and being able to recognize some patterns within your integrals. Solving these integrals quickly will definitely take some practice. You will have to do a lot of examples before you start to recognize certain patterns, and so I would recommend that you practice with more examples if you're still a little bit confused on how exactly you should manipulate these integrals or how exactly you should integrate them. All right, and so if you're looking for more examples, feel free to check out my examples video that I'll have linked at the end of this video as well as in the description below. If you have any questions, feel free to leave them in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.